Right, so in this lecture, we're going to introduce the cascoding current mirrors because by putting all these NMOS together one by one, just on top of each other, it's going to increase the output resistance of the current mirror's output stage, which is pretty useful. Right, so now let's see how we can design this. Right, cascoding current mirrors. Cascoding So the idea starts from this. If we draw one single NMOS and we bias this NMOS using a voltage called V bias N, and we provide a VDS as well, a voltage over here, and you know that the ID, so the IV curve looks like this. This is VDS. It won't be super flat. The reason is it's not the perfect current source. There will be a slope over here will give you a finite output resistance. So the slope here is 1 over RO. RO is the output resistance. Okay, it's 1 over RO because it's I over, the slope is I over V, right? So that's why it's 1 over RO. And we hope RO to be as large as possible, which means we hope this curve can be flat, not something like this. We hope it is flat, and if it is flat, you can imagine that the slope will be way smaller, which means R will be larger. Okay, so we need a so in this curve we can get a conclusion that we need the curve to be flat. IDS, then we need a large RO. Okay, but however, if you only have one NMOS, it's not super large. RO is not that large. You have a slope, you have a ramp over here. If we model this NMOS, you can see that this NMOS is actually a current source being connected with a RO over here, and also there's a voltage source being connected to the NMOS transistor. That's VDS. Okay, so that's D, that's S. This is how we model that. You may want to ask, why can you model a current source in parallel with the output resistance? Why is that? I think the better way to understand this is to think about just injecting a voltage or a current into this part. And because the current source can be considered as a disconnect circuit, so this is the only resistor will be connected to the circuit afterwards. So that will be the output resistance. Okay, and if you put this current source in series with resistance, when you disconnect the current source, you disconnect everything. So this is how you model this current source. So the current source has a output resistance in parallel with the current source. This is not an ideal current source. This is how you do this. And in this model, you can also find out the output resistance RO equals to RO. Okay, and this one is equivalent to this. That's how we model that. All right. So, given this conclusion, and we are trying to find out how we can increase the output resistance of the NMOS. So the way to do that is we can put two together in series. It's called Cascoding NMOS. Yeah, let's start from the next page since there are a lot of calculations involved. Okay, so the way to draw that is like something like this. That's how you make a cascoding NMOS. And because we are doing AC analysis, right? So because it's not a when we are talking about RO, it's always trying to get the AC gain. So we are doing AC analysis, which means you can feel free to ground the VGS, which is a DC source. You can feel free just to ground it. And the way to find out the RO, right? So because this is a black box, you don't know what is inside. So the way to find out the RO is usually we are trying to inject a current. We connect the voltage to the black box, and there will be a current showing over here, just right out the outside of the box. And now you can use this equation to find out the output resistance of the circuit. So this is the we are going to use this a lot in the future, but maybe not this class. But in the future, if you are taking some advanced analog courses in graduate school, you are going to use this a lot. So the way to test the RO is trying to connect the voltage. It's a testing voltage. So that's a testing voltage. To the output and trying to measure the current, IT, and then use VT over IT since this is given and this is measured, and you can find out RO. This is how you can test your output resistance. But right now we are not doing any simulation measurement. What we are trying to do is we just assuming we have a VT and then we got IT. Now let's try to calculate what is the overall RO over here. We won't know, but we can at least list the equation to represent RO in terms of VT over IT. Okay, RO, and there will be a little VGS one. So this is M1, this is CMOS one, and that's a little VGS2 because this is M2. And now I can find out, actually, this is ground to ground, even though it's talking about the AC analysis for this NMOS, but the thing is they have two DC ground being connected to the two terminals of VGS1. So there's actually no current, no IC current can flow through this being generated by VGS1. Okay, but there's still a AC current over here, which is IT only. But the thing is, this part is not active. It's not a current source. There's no current source over here. It's totally just a RO. So we know that IT is flowing into the box. So this is still IT, still IT. Over here, there will be two branches, and merged to one branch again. This is also IT, and there's nothing in there. So IT only flows through here and come back to there and then go to the ground. Okay, so we can find out that this part, because there's an active component, which is the current source in there, so this part is equivalent to this, like what we just drew on the first page, right? This is VGS2 GM, that's GM to VGS2. That's the current source, and that's IT. That's IT as well. And then connect to what? RO. So that's the equivalent circuit. All right. And of course, VT over here. So now let's list all the equations and see what's going to happen. Okay. So the first one, since we know that based on this equivalent circuit here, so that's plus minus, what is this voltage? VGS what? VGS2. Okay, so and this is grounded. See here, this is grounded. So what's the voltage over here? Because this is VGS2, so the voltage at this point compared to the ground will be minus VGS2. All right, and you know a current over here, know the resistor, so you can directly write down this. VGS2 minus VGS2 equals to IT times RO. Because the IT is flowing through RO, and here's the voltage. That's the first equation on the list. What about the second one? You're looking at here is a current divider. So IT actually equals to what? GM. Let's assuming they have the same GM. So GM VGS2, which is a current over here in this branch, plus what? The current in this branch. What is that current? So that current is this voltage minus this voltage over RO. VT minus VGS2 over RO. So these are the two equations you can list in this equivalent small signal model. And keep in mind what you want to do. So that's the final purpose, right? Find out VT over RT so you can get RO. So you want to get rid of VGS2, definitely, right? So the way to do that is substitute all the VGS2 here and here using this one. So IT equals to GM VGS2, which is at a minus sign in the front, IT times RO plus VT is minus plus, but finally still minus IT RO over RO. Right? Because we want to get this one, we are not trying to calculate either VT or IT. Okay, so in that case, we don't care about the VT and IT. We have this equation. We can divide IT on both sides of the equation, and we are getting 1 equals to minus GM RO plus VT over IT minus RO, and we're going to calculate this, which is 1 plus GMRO times RO plus RO equals to VT over IT equals to RO. All right, so right now we can do one more step to find out a simpler version of RO. So RO equals to what? So it's going to be RO plus GMRO squared plus RO. So the thing here is RO is pretty, compared to RO squared, RO is tiny. So this overall thing over here is pretty close to GM RO squared. So we find out that if you put two NMOS together like this, you are getting this. But if you only have one, and you are getting this. Imagine that if RO equals to 100 ohms, this will be huge. This is still 100 ohms. So this is like hundreds of thousands of times more than one NMOS, one single NMOS in terms of the output resistance. So you can imagine that if you do a simulation, the V voltage versus the current at these two terminals will be more flat, right? It won't be like something like this. It will be a lot better. Oops, just touched something by accident. All right. So now we know that we want a cascoding structure to increase the output impedance, output resistance, right? So where are going to use this? You're thinking, hey, I'm gonna use it somewhere, right? So where are you going to use it? Let's take a look. So for the current mirror, we introduced the first one at the very beginning, which has a voltage source, has a resistance, which is trying to bias your reference NMOS, and this VGS is going to be passed to this output stage and draw a current from the load. So the load is powered up by VDD as well. You'll need a voltage source, of course. So that's the original version, right? But the problem is, we hope when this voltage is changing, this voltage is the voltage applied to the VDS. So when VDS is changing or VDD is changing, we hope it's not like this. However, the current, for example, this is IO. We hope the current of the IO is more flat, like this. So how to figure that out? We just introduced that concept, right? So instead of using this, we are trying to use something different. So this is providing a current to your original stage. So you might be thinking that, hey, this might be the solution to solve the problem since I'm having a cascoding NMOS at the output, right? So this is gonna draw a current IO from the load and VDD. Yeah, so this is one of the solutions, but however, this is not the best solution, okay? And now let's think about why. Why is that? Why is not a best solution? So the reason is we hope our final op-amp has a wide swing. This is not a wide swing design. Remember in the lab, when you are working with op-amps, you hope your output can swing rail to rail, right? So you can amplify your signal in a wider range. But however, what you hate is whenever it's approaching this bottom rail, it's getting cut. Right? But you were wondering why is that? You never get figure out why. So now you find out. So that's starting with the problem. Okay. We hope this part to be as small as possible. So what is this part? Just to remember that the differential pair. So for example, let's do a differential pair with a current mirror load. A little bit different. So these are the two inputs of the op-amp. Actually, this is, I don't know, I forgot. I think this is V minus, this is V plus. So that's the two terminals of the op-amp. And the current source, right now, remember, to make it practical, you cannot put a current source into the IC chip, right? So the current source has to be a current mirror. Because we want to increase the output resistance, so we have a cascoding current mirror. And we want to bias, we have to pass the VGS to this output stage. So you need these guys to do this job. All right, and here's the original current source to bias your 2NMOS cascoding current mirror over here. So the problem is, if you have this structure, the voltage over here, remember that's you have 2.5 voltage to provide an DC offset to your AC signal, remember? You have this 2.5 volts, for example, DC. But however, this is VG, right? So this is not VGS. Why? Why is that? Why is VG but not VGS? Because this point here is not ground. This is VS. So 2.5 volts is not actually the overall VGS to turn on these two NMOS, right? But instead, it is just the VG. If you want to get VGS, you have to use VG minus VGS equals to VG minus VS. The problem is you only have 2.5 volts to turn on this NMOS. If you have VS equals to 2.5 volts, can you turn on your NMOS? Of course not. You'll never be able to turn on the NMOS. So it won't be that extreme. It won't be 2.5 volts, but you don't want this VS to be large, right? So you hope VS to be small. So you can have a wide swing range for AC. You're wondering, I couldn't imagine why, because it sounds like it's too abstract. Can I explain why this will affect the AC swing? So if we draw a picture of the IV curve, if you draw a picture for the IV curve, VDS, right? And that's IDS. If you bias your these two transistors at this point, and I think I should like here, and for example, here's VDD 5 volts. That's the upper limit. That's the top rail, okay? And for example, you are you biased your VDS. You biased your VDS to this point. That's VDS. Yeah, actually, it's not a VDS. We are calling this one to be VO. So it's an overdrive voltage. For example, if you bias your the VDS equals to VO overdrive, then here is the upper limit, right? And you can provide a DC offset, 2.5 volts, whatever. You can do a DC offset over here. I don't know, probably it's not 2.5 anymore because it's not right in the middle. So the full range for you to swing your AC signal is something like this. However, if you bias your transistor right after this child region, and here's VDD still, and you can swing your signal like this. So definitely, which one has a wider range? This one has a wider range, wider swing range. The other benefit by doing this is you are using a lower voltage to operate your transistor, so it's consuming lower power as well. So that's why we really want to pursue this final result for your for the biasing. So, but how to reach here, right? So that's the question. How do we do that? If you look at this part, if you look at this circuit, is this a wide range? So it's not a wide swing range design. Why is that? So why that one is not a wide swing range design? For this and label all these voltages. Here's a current source. So current source can be replaced by a PMOS device, in the future. We just drawing a current source right now, just make it simpler. Since that's not a important part for now. Okay, that's IO. Because this guy is symmetric. This guy is symmetric. And if we call this to be VGS, we label this as VGS, which equals to VDS set plus VTH. Then the voltage over here will be the same. It's going to be VGS as well. And because it's symmetric, so this voltage will be mirrored to here as well, which is also VGS. So what is VGS? VGS equals to VDS set plus VTH. So this is pretty large. Why is large? Because we only need a VDS set, but however, it's adding a VTH to it, which is something around 0.8 volts, which is a lot. So it's adding a lot of voltage to this point, and you have another one stacking on the top of this one. So, and you want to keep this one at the saturation region as well. So this point, because after this point, it's getting easier because you only need to add another V overdrive voltage, which is same as VDS stat over here. So this will be VGS plus VDS stat. No problem. You can just add one VDS stat across this transistor to save your voltage. But the thing is, you have to add the same voltage across this transistor as well, which is giving you something large, at least 2 VDS stat plus VTH. So that's a lot of voltage, which means if you connect this one to your op-amp over here, so VS is going to be at least this voltage, right? So it's limiting your swing range because it's already lifting this VS to a pretty high level, which is you can look at the curve over here, which means it's lifting your voltage. Or you can say it's pushing this NMOS deeper into the saturation region. It's pushing this NMOS deeper into the saturation region, which is lower the swing range. Okay, which is undesired. You don't need that. You don't hope this will happen at all. So we have to try. We want to try to decrease the VDS, the overdrive voltage over here and here, to make the overall voltage as the two terminals smaller. Okay, what's the minimum? What's the minimum voltage you can put here and here to make it saturate? Of course, VDS set. So you just need two VDS set at this point. If that two VDS set can keep both of these two transistors saturate, you will win. That's the final purpose. But however, over here, you cannot do that because this point is already pretty large, right? So after you add another VDS set from this point, you get an overall 2 VDS set plus VTH, which is large. So this is not good design. Not a good design. All right. we have to find out an alternative way to figure out this issue. And what is that? Right. Take a look. So the way to do that is, because if you want to self-bias your these two NMOSes by this gate drain connection NMOSes, you have less control of this VGS for these transistors. So the way to figure this out is we are trying to bias these two NMOSes separately using two current sources, and we hope this will solve the problem. So here's one of the current source, and we have an NMOS here, and another current source. Since we want to bias these two NMOSes separately, so one here, and they are being shorted together and being biased by a voltage called V bias P. In the simulation in this lecture, we're going to just directly use a voltage source directly being connected to these two PMOSes to turn them on and bias them right at the boundary of the child region and saturation region. And now that's the first NMOS at the bottom, and we have another one here. So we use this one to bias this guy, and this one to bias this guy, and that's IO, right? So that's a wide swing, or it's called a low voltage cascoding current mirror. And why is that? Because right now you have totally you can control the VGS separately by these two current source. How I can do that, right? So now let's start from here. Let's call it VGS. So this VGS will bias these two transistors correctly, for example. And here is VDS set. It's one time of VDS set. So what's the voltage here? It's also VGS. And what about here? We can control this resistor, this NMOS, to make this voltage to be exactly VGS as well. I mean the difference between these 2 points to be VGS as well. So this voltage has to be VGS plus VDS set. The reason is, you use this gate voltage minus this source voltage, you are getting VGS, one time of VGS. So this is VGS plus VDS set, and it's not affecting anything over here for this overdrive voltage. So this one has to be larger. The smallest value for this point has to be 2 VDS set to saturate both transistors over here in this cascading structure. And this is the smallest voltage we can reach, right? So we don't need a 2 VDS set plus VTH as a previous example. In here, we can control these two NMOS separately in order to reach this one. I mean, it's not like you just use whatever current over here and you can reach this level. You have to adjust this voltage, this transistor to make this happen. And we are going to run through this in LT-SPICE as well. Now let's label these transistors. This is M1, M2, and we call this M4 because in the future there's another one to be added over here. So we are not trying to, we just want to keep all these names of the transistors consistent. And this is called I'm Y swing. And this is M5A, M5B. Right, and in this circuit, the parameters are like this. So this is 1 micrometer technology, and 2, all the NMOS has a size of 10/2, 10 micrometers over 2 micrometers, and PMOS has 30/2 for the size. So now the question is, how can you have the current flow through here, REF, to copy that voltage to here and here? So what's the requirement for the size of this voltage? So now let's find out. So the equation to derive this one is still the square law equation, and we are trying to design the I over here, and this is 1 time of VGS. Okay, this current is REF. This is IREF as well. This is also IREF. Okay, but however, the VGS is different from the VGS over here. So this is just one VGS. But however, this VGS for this transistor, for this wide swing transistor, is not VGS. So we have to change something. Right? So now let's list the equation. So IREF equals to we are looking at this NMOS transistor equals to KPN over 2 times the width of the MWS over the length of MWS, and what is the VGS? So the VGS over here is VGS plus VDS set. So that's the VGS minus what? Minus VTH square, right? So if you compare this one to the original, to this current, which is REF equals to KPN over 2, and this is VGS minus VTH, we must find the relationship between this part and this part. And what is that? Since we know that this equals to what? KPN over 2 WMWS LWMWS. What is this? This is MOSFET wide swing, right? This is transistor. And this part, what is this part compared to here? So it is times what? Times this one. VGS. So this is VGS minus V plus VGS minus VTH minus VTH. Because this one equals to this, right? And what's next? So this equals to KPN over 2 and times 2 times VGS minus VTH and square. Okay, and we need this guy to be IREF as well. And what's going to happen? What's going to happen over here? So IREF equals to KPN over 2 VGS minus VTH. That's the original circuit. And this also equals to this, which is KPN and times 4, because you take 2 out from this square, and VGS minus VTH. Find out all the rest of the equations are the same, so only this part are different. So we can get a conclusion, which is this. And you are not trying to change your, but you can change the length over here because this is a special structure. So definitely, in practical circuit design, we usually don't change the length of the transistors. So the way to do that is if you want to decrease the current, you can use a wire to steal some current out from there to increase the voltage. Thing is fine. So we are modifying this transistor, this wide swing transistor, to lift the voltage of this one to make this one saturate. This is the conclusion, right? So how do we make this happen? How do we make this happen? So 4 times of this one equals to this. How that works? If you're not changing the width, you got to change the length, right? So which means L equals to what? L equals to Lm over 4. So which means the length, no, is that right? Over 4. So the length of this transistor is way larger than L. So 4L equals to L wide swing transistor. All right. So the original NMOS transistors, remember, they are NMOS for the rest of the circuit. All these NMOS, they are 10 over 2. So for NMOS M wide swing will be 10 over 8. Right? This is how they'll design the circuit, trying to make it work. So after change the wide swing transistors ratio to be to this, and you are able to make the current equal in all these branches. Keep in mind, for NMOS, for the rest of the NMOS, they are 10 over 2. For the PMOS, they are 30 over 2. And after this point, this design definitely can be used for the C5 technology in your layout. But however, in some other applications, for example, the short channel design, this won't work. The reason this won't work is you are not getting a equivalent voltage as this drain, these 2 drains, and which will saturate, which will move M4 into the trough region and giving you a smaller output resistance. So which is not really good. And we can explain this in the next lecture because it's going to be too long. And we are going to do some simulations as well. But that one will be shorter. And so in this week, in these 3 lectures, we are only focusing on current mirrors, but nothing else. So make sure you can digest all these contents we have covered in these 3 lectures. All right. So this design again. This design is good for long channel technologies like the 1 micron technology, 1 micron technology for the simulation, and also the C5, which is a 500 nanometer technology for the layout. We can actually fabricate using C5 technology. But it's not applicable to the short channel technology like the 50 nanometer technology for the LT SPI simulation. We're going to look into that in the next lecture. Right. See you in the next lecture.